everyone, we are Team 65 from Section 5, and this is our GEARS proposal in response to the design request from L3Harris. To start, the design team was tasked with constructing and coding an autonomous device that would be able to provide aid to communities and regions affected by disasters. Whether they be man-made or natural, the Global Emergency Autonomous Response System, or GEARS, should be able to transport cargo through difficult terrain to those in need. The delivery of such supplies can be difficult due to damaged infrastructure, remnants of conflicts such as mines or explosives, or any cultural or language barriers. So the design team set out to prototype a safe and effective way to deliver supplies in dangerous zones autonomously and transport the supplies that it will be carrying. The GEARS will be carrying supplies ranging from shelter, food and water, fuel, or medical supplies. To sum up the project objectives, we were tasked with creating a GEARS with the listed capabilities. We would need to develop a model that could precisely navigate through damaged areas, which may be foreign to the GEARS. The GEARS would have to locate and characterize any hazards in the area and transmit a map of the path taken through the environment. Lastly, the GEARS would need to drop off the contents of the cargo and deploy them to those in the area and communicate with them in a non-hostile manner. To overview our presentation, we will discuss our project management protocols as well as our mechanical and software design logic, and there will be a final discussion of our performance and where we feel our model may need to be improved in the future. To start, we will discuss our project management. Here we have our work breakdown structure that lists all necessary tasks and their corresponding subtasks. We reference this often to remind us of the functionalities that we would need to achieve. Next is our Gantt chart, which was used to set up deadlines and checkpoints for us to meet during the entire design process. Lastly, as a method of decision-making and design brainstorming, we formulated a list of technical requirements for the GEARS given its necessary functionalities. These included target values for sensing capabilities and various physical characteristics of the GEARS that we would like to achieve. In terms of the design, we created a morphological chart to decide how we would like to achieve the main mechanical components of the GEARS, and we divided the GEARS into three main parts physically: the drivetrain, the base, and the cargo deployment mechanism.
When first conceptualizing the GEARS design, the necessary technical requirements, our team focused mainly on hazard detection and ease mobility. In order to maintain a minimum distance of 2 centimeters between non-traversable terrain, we knew ultrasonic sensors needed to be mounted on the sides and the front of the GEARS. These sensors output the distance between the device and the objects in its pathway, so any terrain in its pathway would be detected. In order to drive around and avoid the terrain, our team knew a 2-motor powered driving system would be necessary for minimizing the terrain radius while also reducing friction opposing its motion. Looking at the right figure, the yellow represents these motors and the purple represents the stability point necessary to prevent teetering. The stability point was needed to uphold the device and not create a large frictional force with the ground. If the stability point was made from rubber tread, the powered wheels would rotate and turn the device about its center point. Instead, the rubber's frictional force with the ground would apply torque to in the opposite direction of the GEARS' angular velocity. This would prevent smooth, eased turning. Therefore, removing the rubber tread from the wheel and leaving its inner rim would dramatically reduce that frictional force and allow the device to turn with very little opposition. The large white box from the previous slide was our initial idea for a cargo container. It was going to be large enough to hold any life-size cargo along with the battery in the pod. After further investigation, our team determined the size of our cargo container was to be a maximum of 6 centimeters by 6 centimeters by 8 centimeters, and therefore, as seen in these images, a space in the front of the device was set aside for this 3D design container. Some positive features of this first iteration included successful turning, as the 2-motor powered system with the treadless wheel stability point allowed the robot to maneuver with better precision. Also, with the platform designed to hold the pie holder, and cargo container, the initial design had a sturdy foundation in order to hold the necessary cargo weight. Finally, the ultrasonic sensors and IMU sensors were optimally placed for ease of detecting hazards, and magnets representative of high electrical activity. Some negatives included the lack of cord management and a lengthy posterior. Both of these unfortunately meant that the GEARS prototype would hit walls as it turned and brushed up against hazards. Also, this prototype turned based on time. The motors would run at a certain speed for a specified amount of time, roughly turning in multiples of 90 degrees. This unfortunately had a large margin of error, especially on surfaces that were disleveled and caught the stability point during the turn. Finally, this device had no ability to drop off the cargo container, only the ability to keep it on its platform. With further testing, analysis, and tweaking, our team determined the navigation system needed a gyro sensor, a sensor which outputs angle displacement. For precise turning, this was necessary because it ensured the gears would not over or undershoot specific turns, especially around sharp corners or when turning around completely. Then, during testing, our team also built a slanted ramp system and a motorized arm on the front of the cargo container for the cargo container to be held and dropped off properly. The motorized arm would stiffen and lock the cargo container into place while the gears would maneuver through the destroyed area and then rotate down and out to the side, dropping off the container at the location of the recipient community. The slanted ramp used the gravity acting on the container to slide off and onto the ground when the motorized arm rotated out. This kept the cargo from spilling out of the container and the container from sliding off the device while driving through the train. Finally, testing also meant being able to move around sensors for optimal placement. The IMU sensor and IR sensor were both moved to the very front beneath the cargo container in order to detect hazardous zones and dangerous activity, and the ultrasonic sensors were kept on the sides and front of the device for detecting the walls representing terrain. The battery holding structure was removed from the posterior and the cords were wrapped and managed to prevent any contact with the gears and any hazard it encountered. The final gears design seen here has a few unique features, such as the motorized arm, which holds in the cargo container while the device maneuvers the damaged area. The two motor drive and stability point were used to optimize navigational precision and reducing the turning radius and frictional forces, and the cargo container ramp was slanted for the container to drop off at the recipient.
So for our maze solving algorithm, we first chose to use the left wall maze solving algorithm. So this algorithm follows the left wall at all times and is guaranteed to get out of the maze if the maze is solvable. So first, the gear will check if the left wall is greater than 40 centimeters away from the robot. If it is, then the robot will move forward until it clears the corner before turning left. If the left wall is closer than 40 centimeters away, the gear will check if the front wall is within 30 centimeters, and if the right wall is further than 40 centimeters away, turning right if both of those conditions are true. Otherwise, it will check if the front wall is within 30 centimeters and the left wall is greater than 40 centimeters, and it will turn around if it will turn right if that condition is true. It turns around if the previous condition is true. Sorry. So for detecting magnetic hazards and heat sources, the gear uses the IMU's magnetometer and the IR sensor. If the IMU or IR sensor values are detected to be greater than 250 milligauss or 80 respectively, then the gear will turn based on a modified version of the left wall following algorithm. All the conditions being checked and actions taken will be the same, except the gear will not check for a front wall because the hazard will replace the front wall in this case. Likewise, the hazard's parameters and type will be stored to be later written into the hazard file. To store the gear's position, a matrix of zeros of the size of the maze is created, with the robot's starting position and starting direction included as input. Then the gear follows the maze following algorithm to go through the maze. Likewise, a list of hazards is created to store the hazards and their parameters, and both objects are written to separate files at the end of the program. After checking all of these conditions, the robot moves forward until it travels 5 centimeters, and increments a counter variable which starts at 0. This loop repeats until the robot has traveled 1 unit length of the maze, which is adjustable based on input, and then the counter will reset and the robot's position in the maze will be updated based on the gear's direction and current position. This loop continues to run until the gear is outside of the maze. And then the flowchart is on the next slide. And so first, the gear takes input parameters for starting direction, map unit length, starting position, and course dimensions. Then it creates a map of the course and a list of hazards inside of it. Then it first checks if it's outside of the maze, using both the current position variable and the sensors to determine if the gear has left the maze. If the gear thinks it has left the maze, it updates its exit position and deploys its cargo. Otherwise, it checks the magnetometer and IR sensor values and turns based on the left and right wall distances around the gear at the time at which it detects the hazard. If there are no hazards, then it moves forward until and checks the left wall following algorithm values. Turning left if the left wall is not present, turning right if there's a left corner, and turning around if there's a dead end. Then it checks if it has traveled 1 unit length of the maze, if the counter is equal to counter max, updating the matrix map if that is true, and then resetting counter to -1. Then the robot moves forward until it has traveled 5 centimeters and increments the counter by 1. At the end of the program, the gear writes the matrix map and hazard map to the respective files.
Moving on to our results and conclusions, we're going to first talk about some of the positives of our demo. Overall, our gears performed very well during the final demo. It was able to execute very tight 90-degree turns whenever a wall was sensed. It was also able to complete precise 180-degree turns whenever a hazard was detected. When our gears came across both the magnets and the IR beacon, it was able to detect the hazard, complete a 180-degree turn, and continue in the opposite direction. Our gears was also able to successfully adjust its path while running. If the gears ever failed to complete an exact 90-degree turn or ended up too close to the wall of the maze, it was able to correct its direction to continue on a straight path through the maze. This feature was essential to the success of our gears as it corrected errors in the turning mechanisms before they could cause any problems. If the gears had not been able to correct its path in this way, it would likely have run into many walls, hindering its ability to get very far in the maze. Another success of our gears was its ability to keep the cargo container on the robot for the entirety of the demo. Had the cargo been offloaded during the demo, the container also would have been able to keep the cargo contained. Finally, we were able to output a maze to users to indicate our path that our gears took through the maze. Next, we're going to discuss some of the negatives of our demo. One difficulty that our gears ran into was the one pictured here. It ended up running into this wall multiple times during the demo, and it came to a realization later that the gears was sensing the wall in front of it too soon, and which indicated that it should turn left too early. In order to solve this problem, we would just have to lower the front wall sensing threshold so the gears would not be sensing walls too early and turning when not necessary. This would not be a difficult thing to change, it was just not able to be done in the moment. While it is likely that our cargo offloading mechanisms would have worked successfully, we were not able to test them in the final demo. The only issue we could potentially see occurring with the unloading would have been offloading the cargo in an upright position. It would have likely taken a few tries to get the cargo unloaded in the correct orientation. So overall, our final discussion ends with the fact that mechanically our robot was very well built. There's not much we would change about the way we built our robot. It was very compact, which kept it from hitting walls, and it allowed it to make tight 90-degree turns without running into anything. Our code also allowed for fairly precise navigation of the maze. Like I said before, 90-degree turns were very precise when a wall was sensed, and the 180-degree turns were also very precise when a hazard was sensed. We were also able to successfully output a map when going through the maze, and the cargo offloading system would have been successful had we been able to implement it. While this wasn't able to be demonstrated, we are confident in the abilities of this system. We would have maybe had to change the orientation of our box to make sure it was offloaded in the correct orientation. Some tweaks would have been made to the code to make sure that the gears was able to function completely how it was supposed to, including more precise thresholds for checking for walls, so the gear system wasn't turning when it wasn't supposed to. And also, we weren't able to correctly output a hazard message when we did run into hazards, so a slight tweak in the code would allow us to output that correctly as well. And then we would have to perfect the offloading mechanisms to make sure that they worked properly and were implemented exactly when the gear system did exit the maze, and also allow for the offloading of the cargo to be in the correct orientation.
That is all for our gears presentation. We appreciate you listening and hope you have a great rest of your day. Thank you.